Good afternoon. Where is everybody? Looks like a good day for a quiz. Do it! Do it! We got to a spiffy example last time, but we were cut off rudely by the 2 o'clock cuckoo clock. And that example was the notch filter. The frequency response of the filter we ended up writing out, and it turned out to be this expression. Now, just to show you how I did the reverse engineering right at the board side, if I want to go from here to the difference equation, what I'm going to do is multiply top and bottom by all the negative powers, or by the highest negative power, or by the least negative power of e to the I omega, such that I don't see any positive power of e to the I omega. So I get, and that in this case would be e to the minus I omega. If I multiply top and bottom by e to the minus I omega, I get 1 minus e to the minus I omega over 1 minus 0.99 e to the minus I omega is equal to h of omega. And when I cross multiply, of course I do this stuff in my head when I'm writing this stuff, and you should get quick enough with it so you can do the same thing. And now if you just add or multiply both sides by e to the I omega n, you will see where this came from in the time domain. So you have on this side, you have e to the I omega n minus e to the I omega n minus 1. On this side, you have e to the I omega n h of omega minus 0.99 e to the I omega n minus 1 h of omega. And remember, when we had, I'm trying to get back to the difference equation. When we went the other way around, when we went from the difference equation to the frequency response, we plugged in x of n equals e to the I omega n. So x of n minus 1 was what? E to the I omega n minus 1. And the corresponding output was what? This goes in, what comes out? H of omega times the same complex exponential. So y of n minus 1 will be this complex exponential times h of omega. And now you recognize all of those terms in this equation. That's how you make the connection. So this term corresponds to what? Y of n. So now I'm going from here to here. And this term corresponds to what? Minus 0.99 y of n minus 1. And on the right-hand side, you have x of n minus x of n minus 1. And there you have it. So that's the difference equation that leads to that frequency response. And being able to go from one domain to the other is important. You'll get much better at it when we do Fourier transforms. But you should still be able to do it now using this heuristic method of recognizing that when you plug in e to the I omega n, you get the same complex exponential out scaled by h of omega at the output. And then the rest of them correspond to shifts. OK, so let's get back to that frequency response. I'm going to bring it back down. So in the numerator, I have a complex number for any omega. Pick your omega. So you're somewhere on the unit circle. For any omega, this white vector would be e to the I omega. So for any vector, for any omega, you're somewhere on the unit circle. E to the I omega minus 1 will be which of these vectors? Huh? The blue. Going from here to here. And the arrowhead is always on the one that doesn't have the negative. And the red vector corresponds to e to the I omega minus 0.99. Now, of course, I've exaggerated the distance between the x, the red x, and the blue circle. But they're very close. Okay? When I want to figure out what the magnitude response is of this filter, I'm looking at the magnitude of a ratio, which is what? Ratio of the magnitudes. Which is essentially the ratio of the blue vector over the red vector. Okay? Now, when these two are pretty close, what can you tell me about the ratio of those two vectors when I'm sufficiently far apart, far away from omega equals 0? They're approximately equal to 1. So let's plot. So for approximately equal to 1, for omega sufficiently distant from 0, or omega equals 0. So this is omega equals 0, and all I care about, because this is a discrete time system, is one interval of length 2 pi. So I'm going to worry about the interval from minus pi to pi. So as long as I'm sufficiently far away from a tiny neighborhood around 0, you're telling me the magnitude response is approximately 1. Okay? Now what happens is I approach 0 from either the positive side or the negative side. So I'm going from minus pi to pi. So I'm approaching 0 from the negative side. As I get closer and closer, which one of these two vectors is going to dominate the scene? Really? What's going to happen when I go to 0? The blue is going to dominate. The blue is the one that's going to 0. This red one is always going to stay finite. It's going to get small, but it's going to stay finite. It's the blue one that's going to go to 0. And what happens when the magnitude of the blue vector goes to 0? When I'm right smack on this number 1. It's 0. So it starts dipping, 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 dipping until you go to 0. And then it starts rising again as you get away from 0. The closer this x is to the unit circle, the sharper will be the dip, and the better the notch filter. But from a practical standpoint, and this is something that you won't really get a good grasp of until you take 120. From a practical standpoint, you can't just arbitrarily take this close to the unit circle, because in the real world, systems get perturbed by temperature, by all kinds of environmental conditions, by numerical errors. And if because of any of those conditions, this x, this 0.99, or however close you want to take it, suddenly hops over to the outside of the unit circle, you're going to have a problem. You're going to have instabilities. But that's not something we worry about in this class. So as far as we're concerned, as long as this x stays inside the unit circle, in other words, this number is less than 1 in magnitude, the closer you take it to the unit circle from a theoretical standpoint, the sharper will be this dip. And the cleaner will be your notch filter. Now, what does this notch filter do? Why do we call it a notch filter? Well, yeah, the magnitude response will look like a notch in the, we'll have a notch in the middle, but from a, what is it doing to the signals? It kills the signal that's been notched and passes everything else as an equal opportunity filter. Okay? Doesn't care about what the others are. In terms of magnitude, the phase will invariably be different for different frequencies. But in terms of the magnitude, the amplification that it sends each of these frequencies, it doesn't care where you are in the spectrum as long as you're not 0 or a very tiny neighborhood around 0. So if I give you a signal that's like this, e to the I pi n, what's going to come out? Talk to your neighbors. 30 seconds to a minute. Tell me what's going to come out. You shouldn't have to write equations. Need both.
All right. So, for the frequency domain, will you write the 1 as
e to the I 0 n. So hold on. How many frequencies are in this signal? Which ones? 0 and pi. You know what's going to happen to 0. It's gone. It's butchered. So y of n is going to be what? E to the I pi n times what? Is it 1? Hold on to that thought, Meatball. I've got them exactly where I want them. So y of n, you told me it's got 2 frequencies. So what comes out is h of 0, the first frequency, and the second frequency. Right? We know that. It's an LTI filter. H of 0 is 0. So that goes away. That's how Meatball said we eliminate the 0. And what can you tell me about h of pi? Who said close? Close to? Or? Yeah. If you don't want to write any equations, like I told you, what you know is that the magnitude of h, we know, that the magnitude of h at pi is approximately 1. Okay? Actually, I take the previous statement back. You know the magnitude of h at pi is approximately 1. So h of pi, whatever it is on the unit circle, is a value on the unit circle. Now, in this particular case, I picked pi because it gives you a real number. So in this case, what is h of pi? Where on the unit circle is it, roughly? Is approximately. Where is it? That's when you actually plug it in. H of pi is what? E to the I pi is what? Minus 1. Minus 1 over minus 1 minus 0.99. This is approximately equal to? This turns out to be approximately equal to the real number, positive 1. But the main point of the notch filter is that it kills this zero frequency. Okay? If I'd given you the other frequency, if this had been, say, pi over 4, you wouldn't have gotten a real number out. This would have been a complex number. But the point is, its magnitude would have been approximately 1. Now, what if I want to make a notch filter at a frequency other than 0 or pi, and I still want to have a real filter? So what if, let's say to design a discrete time LTI filter, notch filter where the notch is at other than, let's not say other than, let's just say, let's give a concrete number, where the notch is at omega equals pi over 4. And the filter is real. And has the lowest order. By the lowest order, I mean the lowest order that of the difference equation that characterizes it. The lowest order, i.e., lowest order LCCDE. What do we do? Any ideas? Let's play complex tic-tac-toe. I want you to tell me where to put the X's and where to put the O's. Where do I put the first O? Huh? E to the I pi over 4. That's right here. This is pi over 4. Where does the next O go? Negative pi over 4. It's complex conjugate. Last time we said if we want real valued filters, we want everything to occur as complex conjugate pairs. That's how we get the coefficients of the difference equation to be real. And where do I put the x's, people? Next to them in what way? What angle? Pi over 4. So if I want to stay on the same angle and right next to this guy, I put it right there and right there. Okay? So now, if I want to write h of omega I'll have two first-order factors in the numerator and two first-order factors in the denominator. I have an e to the I omega minus what? Somebody listening in on us by phone is very excited. What is this number? E to the I pi over 4. And what goes here? E to the minus I pi over 4. And what goes here? Let's say this radius is 0.99 again. 0.99 e to the I pi over 4. Now you know why we did all that complex number stuff. Because by now you've got to be very fluent about reading off what this value is. I'm writing this number in its polar form. That means I need to know the radius and I need to know the angle. I know both of them. Radius, 0.99 e to the I pi over 4 is the phase term. Well, what made this ratio approximately equal to 1? It was the fact that these two were very close to each other. So when I'm sufficiently distant from the angle omega equals 0, these two vectors were roughly the same.
So by low order, you mean that we're going to have these vectors such that they're going to be...
No, low order is something else. So I get the 0.99 from the fact that, from the desirability of having these two vectors be roughly the same as I'm going around the unit circle and I'm sufficiently distant from this angle. So in this case, I've got two such angles, pi over 4 and minus pi over 4. And when I'm at any point here, e to the I omega, notice what I have in the numerator. I have this vector, which is, sorry, the blue one.
So far our terms have been just based on the fact that we're given notch filters such that it's omega naught.
No, you're designing a notch filter.
Yeah.
So your boss says, design me a notch filter such that when you want to implement it on the computer using the difference equation, whatever it ends up being, and we're going to do that with this. I don't want any storage, anything more than 2 storage units. That means my difference equation has to have at most 2. Or in his case, he tells you, give me the minimum storage. The moment you go off the omega equals 0, omega equals pi angle, you know that to keep the filter real, whatever 0 you put here, you've got to put the complex conjugate. Whatever x you put here, you've got to put the complex conjugate to keep it real. Okay? Now, whatever gets you excited. So now, I'm looking at a filter that I write in factored form for every term that I have here. For an e to the I pi over 4, I have to have a complex conjugate term. That's how I get, when I multiply this out, the coefficients of all the powers of e to the I omega will end up being real. If I didn't have this, then this would be a complex difference equation. If I just had said, okay, let's look at this filter. Your boss says, notch out pi over 4. Okay, I'm going to notch out pi over 4. I'm going to put that there. I'm going to put that there. That'll do the job. This will do the job. But it won't be real. This filter will be of the form g omega equals e to the I omega minus e to the I pi over 4 over e to the I omega minus 0.99 e to the I pi over 4. Write the difference equation for that, and you're going to have these kinds of terms in there, which won't be real. To make it real, you need another pair. For each of these, you need its complex conjugate, and that's what we have in this diagram. So now, I'm looking at the magnitude of this filter What is the magnitude of this filter? I've got two factors in the numerator, two factors in the denominator. You already know the magnitude of a ratio is the ratio of the magnitudes. But what's the magnitude of the numerator? The product of the magnitudes. And same in the denominator. So if I were to write h omega, it'll be magnitude e to the I omega minus e to the I pi over 4. I'm going to separate them in a smart way now. E to the I omega minus e to the minus I pi over 4. And in the denominator, I put the x that's closer to this O. So in the denominator, I put e to the I omega minus 0.99 e to the I pi over 4. And in this one, I write e to the I omega minus 0.99 e to the minus I pi over 4. Now look at this ratio. The way I've placed the x's and o's, what can you tell me about this ratio when I'm away from pi over 4? It's approximately 1. When I'm away from minus pi over 4. So at any point, at all the points around the unit circle that you're sufficiently away from this, pi over 4, and minus pi over 4, this ratio is approximately 1. This ratio is approximately 1. The product is approximately 1 for omega sufficiently distant from plus minus pi over 4. Is that clear? Question?
You now have two notches.
I have two notches, yeah.
Is there a way to rectify that so you just get the pi over?
That's usually for practical purposes, it's not a problem. Yeah. So usually if you want to notch out one frequency, typically you want to notch out the negative of that frequency. Otherwise, you'll have trouble with things like cosine pi over 4n. Your boss wants you to notch out not just e to the I pi over 4n, but cosine pi over 4n. That then dictates that you need another notch here. So as long as I'm somewhere sufficiently distant from this angle and this angle, I have the magnitude response being equal to the product of the blue vectors in the numerator divided by the product of the red vectors in the denominator. Now, if this guy is roughly equal to this guy, this part, I get approximately 1. And this blue vector is approximately equal to this blue vector, I get approximately 1. So the whole product is approximately 1. Now, what happens when I approach pi over 4 from this side or this side? It goes to 0. And what about this guy? Same thing. So my frequency response will be 0 minus pi, and I have a pi over 4 and a minus pi over 4. And my frequency response will be roughly equal to 1, except when I get close to minus pi over 4. Again, goes up. Dips again, goes up. And that's my notch filter. Two notches, one at pi over 4 and one at minus pi over 4. And everywhere else, approximately equal to 1. This is h of omega. Well, if they're not at the same radius, then they're not appearing as complex conjugate pairs. You're going to get a complex valued filter. Yeah.
How do you push out the h of n from that omega?
H of n, you mean the impulse response? Well, the impulse response will be much more complicated for the second order system. Let's do the difference equation first. So actually, you should be able to do the difference equation. All we need is for somebody to tell us what 0.99 times 0.99 is. It's approximately equal to 1. But let's get a number up to 3, 4 digits and see. Do it. You guys are all gadget gurus. What do you have to multiply the top and the bottom by to get the difference equation? E to the negative? Negative I omega? Negative I2 omega. It's second order. You gotta distribute the wealth properly. E to the minus I omega, E to the minus I omega. One goes here, one goes here, and then you multiply it out. So what I want you to do is multiply top and bottom by E to the minus I2 omega. Carry out the multiplication, and then tell me what the difference equation is. I'll give you like 3 minutes or so to do that. And then we'll take a break after this. To keep the algebra simpler, why don't you turn this into alpha and this into alpha star, where alpha is approximately equal to, where magnitude of alpha is approximately equal to 1, meaning alpha is somewhere close to the unit circle. Do we have the difference equation yet? Okay. So who's got it? That can't be right. I didn't ask you if you're confident about your answer. Did you get to a difference equation? You haven't spoken in a while. We'll go with you. And you are? Mark. First you got to? Yeah, so you got to multiply it out. So h of omega is? Uh-huh. Minus e to the I pi over 4. Can you give it to me after you've cleaned it up a bit? You've cleaned up and collected all the same powers of e to the I omega. Do you have that? Okay. Is this alone? Yeah, but is this alone? What's multiplying it? Yeah, but where did e to the I omega go? So, what do you mean there's no I? No, you have to have the power of I. This should be the first order term. You have that?
I actually can reduce it by, it's equivalent.
Okay. Did you make a mistake somewhere? I think you've made it. Yeah, okay, so let's go with you.
Okay. I'll just continue before that. And then that finishes off with plus e to the
plus this times that, which is what, people? 1. Okay, and what is this?
That would be 2 cosine.
I told you need the complex conjugate to make the coefficients go to real values.
All right. Find the denominator. Again, starts off with e to the I2 omega.
E to the I2 omega.
And I actually used the original values. I didn't change the alpha.
Okay, let's use the original values.
Okay, in this case, we find the, using the same style as above, we find the 0.99. Okay, at the end, it'd be e to the I omega.
Mm-hmm.
And the middle will turn out to be the same as above, so it will turn out to be 2 cosine pi over 4.
Let's remove that extraneous parenthesis.
And then at the very end, it's plus the square of 0.99.
Okay? Now what?
We multiply both the numerator and denominator by e to the I negative 2 omega.
Multiply top and bottom by e to the minus I2 omega. So you get 1 minus, let's simplify this, 2 times root 2 over 2. That's root 2. Times what?
E to the negative I omega
E to the negative I omega.
plus e to the negative 2I omega.
Negative I2 omega. Divided by
1 minus 0.99
times root 2.
e to the negative and then plus 0.99 squared e to the negative I2 omega.
Now you have it exactly in the form that you need to write down the difference equation. And what's that difference equation? So the denominator will correspond to the y terms. The numerator will correspond to the x terms. So this one doesn't have an e to the minus I omega. So that corresponds to what?
Or
Y of n. Minus 0.99 root 2 y of n minus 1. Plus 0.99 squared y of n minus 2 equals. And in the numerator, x of n
minus root 2 x of n minus 1
x of n minus 1
plus x of n minus 2.
plus x of n minus 2. And that's the difference equation that governs this. Now, one thing you probably want to do, and I'll leave this for you to do at home, maybe I'll even put it in your problem set, is look at, so notice, by lowest order, I mean a second order difference equation. The largest delay on each side is 2. So this is a second order difference equation. And that's what we wanted. And all the coefficients are real. And that we got by using the fact that by placing these at complex conjugate locations. Yeah, question? You can have higher order, but it would introduce other things in the frequency response. Because higher order means, delay means storage costs. And anytime you have one of these terms, if I had a y of n minus 3 term in here with its own coefficient, I would have had an adder, another multiplier, and another storage element. If you don't need it, why use it? That's the idea. Okay, so look at h of omega equals e to the I omega. Now I'm going to place the notch frequency at an arbitrary frequency. E to the I omega naught. It's not just at, it's not necessarily at pi over 4. At omega naught, I'm going to have its complex conjugate. And then in the denominator, what do I need? E to the I omega minus some alpha, which is real valued and positive. So in this case, alpha is real valued and positive. E to the I omega naught, e to the I omega minus alpha e to the minus I omega naught. Actually, I take this back. Alpha is real less than 1 and approximately 1. Okay? I want this to be in its polar form. So alpha has to be positive. And for this to be a notch filter, alpha needs to be pretty close to 1. So in this case, it was 0.99. So you can, at your convenience, write out the difference equation corresponding to this filter. It's just a generalization of the filter in the top. Except this is for an arbitrary notch frequency, omega naught. Good question?
Is that the most general form we can have for notch filter? For a
two-frequency notch filter? No. Well, first of all, I've ignored a gain factor here. Yeah, let's use A. Okay? This doesn't have to be. Where's mine? This doesn't have to be 1. It can be some other constant. Okay? And there's also, well, it's the lowest order, most general form. If I allow higher order terms, I can have factors multiplying this out whose magnitude is exactly 1. There are filters called all-pass filters. All-pass filters are somewhat interesting. When you look at the magnitude response of an all-pass filter, it's constant for all frequencies. The only thing they do is fiddle around with the phase of the input signal. So this is general modulo an all-pass filter sitting in front. But aside from that, yeah, it's the lowest order, most general form of a notch filter. Let's take a break. And then I'll move into analog filters. Okay, folks, let's move to continuous time. You will notice in this course, I don't follow a fixed pattern between continuous time and discrete time. If you look at textbooks that have been published, they take one of several approaches. Some textbooks proceed in parallel. They do continuous time, then discrete time. Continuous time, discrete time, as they move from topic to topic. Some textbooks do everything in discrete time. Some textbooks do everything in continuous time. The way I do it is that depending on the topic and how amenable it is and how more easily explained and understandable it is in one of the two areas, discrete time or continuous time, I will choose that area. So for filtering, it's much nicer to be going around the unit circle and putting these X's and O's and explaining what convolution is. Convolution in discrete time is much easier to explain. So I do it in discrete time first. But at some point, we have to study continuous time. So let's do that now. I have a continuous time LTI filter. It's got an impulse response and an output. The output I know is the convolution. The convolution of the impulse response and the input. X goes in. Y is H star X of t, which is the integral from minus infinity to infinity, H of tau, X of t minus tau, d tau. This is using the same kind of argument that we use in discrete time. Continuous time LTI systems are entirely characterized by their responses to a Dirac delta. Just like in the discrete time story, the response or the discrete time LTI system was completely characterized by its response to a Kronecker delta. Except now instead of the summation, you have the integral. We want to talk about these systems in the frequency domain and see what happens. Well, what kinds of special signals did we look at when we dealt with discrete time systems? What did I apply to the system in discrete time? Complex exponential. So try x of t is e to the I omega t. Okay? If x of t is e to the I omega t, x of t minus tau is e to the I So I plug it into the convolution expression. So y of t, the output, is the integral from minus infinity to infinity, h of tau, e to the I omega t minus tau. So I put the minus tau here, and e to the I omega t, and then I have a d tau. Okay? What can I do to this complex exponential term? Take it outside the integral, because the integral is over tau. So I have h of tau, e to the minus I omega tau, d tau, this whole thing times e to the I omega t. I have this integrand, which is a function of tau and omega, and I'm integrating over tau. What am I going to be left with? A function of omega. I call that capital H of omega, and that's the frequency response of the filter. So in discrete time, you had summation from minus infinity to infinity h of m e to the minus I omega m. In continuous time, you have the same type of expression except with an integral. That's expected. So the format is roughly the same. So again, we've seen that with an LTI system, when you plug in e to the I omega t, a complex exponential of a particular frequency, into a continuous time LTI system, you get the same complex exponential out, scaled by a complex, typically complex number that's called the frequency response of the filter. So h of omega is defined as h of tau e to the minus I omega tau d tau, frequency response. Pretty much the same as the discrete time story, except instead of a summation, you have an integral. So what this means is that complex exponentials are also eigenfunctions of continuous time LTI systems. When they go in, the same thing comes out, scaled. Now, it's possible for the filter to be such that for that particular frequency, this h of omega will be 0. That means it kills that particular frequency. So a particular frequency may go in but not come out. But you can't have a situation where a particular frequency is not present in the input, but suddenly it pops up in the output. That can't happen. And again, here you need linearity and time invariance for this property to hold. So continuous time LTI systems do not create new frequencies but can kill some input frequencies. What's an example of a nonlinear system that creates a new frequency? I asked this question when we talked about discrete time systems. Y equals x squared. Example of a nonlinear system that creates new frequencies. It's the system that squares the input. So when you send an x of t, you get out x squared of t. So when e to the I omega t goes in, e to the I 2 omega t comes out. Input frequency is omega, output frequency is 2 omega. Can you give me an example of a time-varying system? Example of... So this is actually interesting. This is an example of a nonlinear time-invariant system. The squarer is time invariant. You shift the input, you shift the output. Example of a linear but time varying system that creates new frequencies. Can you think of one? Talk to your neighbors. Think of we have done this as an example in the class before. One of the examples we did early on does that. Okay. What have we got? You are? Tim. Mm-hmm. Time varying but linear, but how does that create new frequencies?
Just yft equals xft plus a constant.
Plus a constant? Y of t. Pardon? Yeah, that's not linear. Any other tries? Look at your notes from the time when we discussed system properties of linearity and time invariance.
Would the yft equals xft times an oscillating function?
Very good. Modulator. X of t multiplied by, let's say, e to the I omega naught t. Okay? So if x of t is at a particular frequency, e to the I omega 1 t, then y of t comes out what? E to the I? You want to get out of here by 2, right? It's not a trick question. Omega naught plus omega 1. So the modulator actually shifts the frequency of the input. This particular modulator shifts the frequency of the input by omega naught. So this frequency goes in, this frequency comes out. And I picked these two examples to make a point that you need both linearity and time invariance to have, for the system to have the property that no new frequencies are created. So I eliminate one and keep the other. So in the first case, I kept time invariance, eliminated linearity, and I noticed that a new frequency is created. Then I did the other way around. I kept linearity and removed time invariance, and new frequencies were created. So you need both of them. Okay, we'll get into analog filters next time.